All right, so all done. We're going to continue with chapter 13. And we will finish it today. How about the super important distribution, the binomial distribution? Right, so suppose, what are the three conditions that you know you can use a binomial distribution to describe it? No?
Probability distribution?
This is a probability distribution. How do you know when to use it?
If two things are independent.
X and a P.
You can repeat the experiment n times.
An experiment is repeated n times. What else?
There's only two possible outcomes.
Two possible outcomes, exactly two. That's what the word bi means, two. Two possible outcomes, which we subjectively categorize as success and failure. Right? Success is just what we're looking for to happen. Failure is just that that thing doesn't happen. Three.
Each outcome is independent of others.
Each outcome is independent. So if you have these three scenarios, these three situations coming together, you can describe that if you want to find probabilities of not just anything. So suppose these three things are fulfilled, and we want to find the probability of k successes in n trials, then if x is the number of successes, that is k, then it is called a binomial random variable. And on top of that, the probability of k successes, the probability that x equals k, that what you're looking for will happen k times out of the n times, is n choose k, p to the k, q to the n minus k, where p, q, what's p? The probability that a success occurs. That's the probability of success. And q is?
Probability of failure.
Probability of failure, which is 1 minus p. This is probability of failure. Right? And this guy pretty much will count the different arrangements. It doesn't matter what situation happens first or second or third of the n times. Your k can occur at any point, and the order doesn't matter, so you can use a combination. And you want the p to happen k times. It's independent, so you have to multiply p by p by p k times. And the q will happen the rest of the time, so you multiply those by because they're independent. So that's sort of what that formula says. And moreover, there are two other pieces of information that you need to know. So you need to know when something is binomial. So this you need to remember when these situations are fulfilled, because like I said, we're not going to tell you it's binomial. We're just going to give you a word problem, and you have to read it and sort of figure out that it is binomial. Once you figure out that those three things are fulfilled, you know it's binomial. This will be the formula to get it. These are what the pieces in the formula means. N is how many times you're doing the experiment. Moreover, we know that mu, the average, right? This is the mean average. Is equal to n times p. That's also something that you need to know. Moreover, sigma the standard deviation is equal to the square root of n times p times q. And basically we went through that whole formula that we have for mu and sigma, which remember we know how to find the formulas for those, using this formula for our p's, and then you can derive that this will be true. So these you also have to know, not only for this chapter, but for the next chapter. That's going to be really important. Right, so this is called a binomial distribution. You're in this situation, you're repeating the same thing n times. There are only two possible outcomes. Each outcome is independent. If you want to look for something to happen k times, right, you're looking for one of these two outcomes to happen a certain number of times, then you can describe it with a binomial random variable. It will be a discrete random variable, has a probability distribution, everything that we were talking about. This is the formula that gives us the probability. These are what all the pieces mean. And if we need to know the average or the standard deviation, these are the forms that gives it to us. So this you just need to know, right? So that's where we picked up, stopped last time. Yeah.
The parentheses for n and k, that means n chooses k.
Yes, this is C, N, K, or N, C, K. It's the combination. So this thing. Remember that's in your, you can use your TI calculator. It's under math, and then you go to probability, and it's either the third or the fourth option. Let's do an example. For right now, we'll do one example because in the next chapter, we're going to come back to binomials. And we will do more. So the basketball player makes 70% of the shots he takes. Assume the shots are all independent of each other. And he makes 10 free throws. What is the probability here's what I want you to figure out. A. He makes all 10 free throws. B. He makes none. He misses all of them. C. He makes exactly 2 of them.
Thank you.
D. He makes somewhere between 3 and 5 of those baskets. And E, he makes at least 1. Okay, so one possible way you can have a question posed to you, again, notice I did not mention it's a binomial at any point, but all the signs are there,
An experiment.
right? He's repeating something a certain number of times. He's repeating something 10 times, in fact, right? It's the same thing. He's making a free throw. He's doing the same thing over and over 10 times. There are, of course, only two possible outcomes. He'll either make the shot or he'll miss, right? So that's the next one. And right here, we're told that we will assume that they're all independent of each other. So we have the independence, right? We have those three situations all packed into this one sentence, right? You're supposed to read that and recognize it. Right? Something that you're always going to be looking for, right? So he's repeating an experiment, making free throws. He's repeating it 10 times, right? Each one is independent, and there are only two outcomes. He'll make it or he'll miss it. Now, given that, what is the probability that he'll make all 10, he'll make none, he'll make exactly 2, or blah, blah, blah. Right, so these now, they're telling me about the number of successes we want to look for, right? And success here is that he actually makes the shot, right? What we're looking for to happen is that him actually making the basket.
But in
right?
the question, it says he makes 10 free throws.
Huh?
Assume the
Well,
shot
he makes like
all
he shoots
independent.
10 free
That's
throws.
the-
Well, he attempts.
That attempts who's buzzing.
Right? So he attempts 10 free throws, right? What's the probability that he actually makes all 10 or blah, 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 right? So you'd read that, you'd see all the signs of a binomial, like, oh, it's binomial. Okay, so now here, yeah, obviously, right? So first we have to figure out what these pieces are, right? We need to know what n is, we need to know what p is, we need to know what q is.
So n is 10.
N is 10, the number of times you're repeating the same thing over and over.
P 7.
0.7.
P is 0.7, right? So it's the probability of a success. Now success here is what we're looking for to happen, right? He makes, we're looking for how many he makes, right? I could have phrased the question asking how much does he miss, right? In which case you could say your P is actually 0.3 because success doesn't just mean success, it means what you're looking for to happen, the thing you're counting, right? So here I want to count how much he makes. So the probability of him making the shot is going to be my P, which is 0.7. The probability of him missing 1 minus 0.7, that's going to be 0.3. Right? So once I realize it's binomial, I immediately need to know what these variables are, right? And they'll be the same throughout all these problems. The only difference is that the only thing that will change here is the k value that I'm looking for, right? So now let's actually go to the first one. What's the probability that he makes 10 shots, right? So here we want, what do we want?
We want the probability
Probability that x equals
10.
10.
10, right? So this is our k value here. Right. Now we know that the probability that x is equal to k is equal to n choose k, p to the k, q to the n minus k. Which means the probability that x equals 10 is going to be, fill in the numbers now. 10, choose 10, p to the 10, q to the n, so this is q to the 10 minus 10, right? Now, if you plug this into your calculators, 10 choose 10 is actually just 1, right? This will be 0.7 to the 10, and this will be 0.3 to the 0, which is also just 1. So this answer here is 0.7 to the 10. Now the reason why I did that is I wanted you to realize that this is actually consistent with a previous formula that we had, right?
What?
Previous formula.
Okay.
Like technically you could have done this even if I never told you about a binomial. How would you figure that out?
0.7 times 0.7 times 0.7.
Right, because independent events, and I wanted to find the probability that he makes the first and the second and the third and the fourth, blah, blah, blah. Independent events and translates to multiply. I would literally multiply 0.7 10 times. I just wanted to show you that it's consistent, right? So even if you saw as a binomial, you do this, you'd still get to this point, but you could have done this without it. Where binomial really comes in handy is situations like these, right? But I just wanted you to know that it does work here. In fact, what's the probability that he makes none? What would that be?
1 is that.
It would just be 0.3 to the 10, right? Let's just go through the motions though, set up the formula, and I'll show you that you'll actually get the same thing, right? And then the rest of them are going to be the, well, C and D anyway. So B. So here we want K equals 0. He has 0 successes. He makes none of these baskets, right? So what I'm going to look for is P of X equals 0, which is going to be, and I'm going to, again, use the same formula. It's always the same formula. 10 choose 0, P to the 0, Q to the 10 minus 0. 10 choose 0 is 1. This is also 1. So the answer ends up being 0.3 to the 10, right? Which is what we'd expect. Okay. So now in C, the probability that he makes exactly 2. Now, hopefully you can appreciate, if you're doing this brute force, how annoying that would actually be. Right? Because how many ways can he actually make exactly 2?
Oh,
It's actually going to be a lot more, right? You can make like the first and the second, the first and the third, the first and the fourth, the first and the fifth, blah, 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 or the second and the third, and the second and the fourth, blah, 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 or the third and blah, right? There'll be tons of ways. In fact, we sort of know how many ways. It'll be 10 choose 2 ways, right? So out of that 10, choose 2 of the ones that he will actually make, where the order doesn't matter. I don't care when he makes it. And that's how many situations you'd have to go through if you're brute forcing it. But the binomial formula actually just gives that all to you for free in one little concise formula. So that's what's nice. So in part C, here we're looking for K equals 2. I want 2 successes, him to make 2 baskets. So P of X equals 2 will be equal to 10 choose 2. I'm looking for 2 successes out of that 10. The probability he makes 2 of them would be 0.7. They're independent, so I multiply 2 0.7s. And the rest of the time he will make this. The other 8 times he will actually miss, which is a probability of 0.3. So you plug that into your calculator.
So it's 45.
Yeah, this is 45. Yeah, you'll need a calculator for these. Just tell me what the answer is.
I got, I don't know, I'm gonna check. 0.001446700.
Okay, does everyone agree with that? 0.001. So it's like 0.15% or 0.14%. Right? So what's the probability that he makes just 2 shots? It's actually very small.
Now, if I was this player,
Huh?
now if I was this player, that would be accurate.
So probably you make 1.
So that's the probability that he'll make.
He'll actually make 2 of the shots that he attempts. Right? So if you shoot 10 times and he only makes 2, it's actually not very likely.
It's more likely that he'll make more.
Yeah, I mean, he has a 70%, right? So technically, if he makes 10 shots, you'll expect him to make close to 7. So the fact that he makes 2 is kind of going to be strange, right? Based on the assumptions that you're making on how he shoots. So yeah. You know someone's average, and this will help you gamble, I guess.
I
Okay,
have a basketball question.
let's go to, what's the probability that he'll make between 3 and 5?
So the probability of making 3
What we
plus
doing? What
probability.
You guys got numbers?
Yeah, D.
You don't got numbers, do it real fast. 44.
What do we want here? How do we express this in terms of a probability?
P of X is equal to 3.
If I only attempt 1 free throw and I can get 100, right?
First you get set it up like this. X is somewhere between 3 and 5 inclusive, right? Now in the binomial, it turns out you also have mutual exclusivity, right? Because these are 3 different scenarios. There's a scenario where he takes 10 shots but he only makes 3, or he takes 10, he'll only make 4, or he takes 10, he'll only make 5. You can't take all of them at once, because then he wouldn't have taken just 10 shots. Right, so we also have mutually exclusive here. So what I'm really looking at is P of 3 plus P of 4 plus P of 5. And I'm pretty much going to repeat that formula 3 times. So for the first one, this is going to be 10 choose 3, 0.7 to the 3, 0.3 to the 7, plus 10 choose 4, 0.7 to the 4, 0.3 to the 6, plus 10 choose 5, 0.7 to the 5, 0.3 to the 5. And that's roughly going to be what? Give me 4 decimal places for each, and then we'll add them.
Okay.
Make sure you practice on your calculator how to do this so you know you're getting the right answer.
The first one's 0.009,
009,
then it goes 001. So this is
10090. Okay.
What is this stuff?
second one's 0.0367.
368. Okay.
I think the last one is 0.1029.
Okay. Add those all together. What do we get?
It's not so bad.
0.1487.
0.1487.
87.
Yeah, so around a 15% chance that he'll actually be somewhere between 3 and 5. Right? Assuming that each time he has a probability of 0.7 to make the shot, making between 3 and 5, there's actually a 15% chance. E, at least 1. We basically want here the probability that x is greater than or equal to 1. That's what at least 1 means. So what do we do here?
Can we do
The
just
probability.
less than 1? So
Right.
C.
Right. So again, if we go by this strategy, we'd have to add all the ones from 1 all the way up to 10. The opposite is easier. We use the complement. 1 minus the probability that x is less than 1 is what we would use. There's only one way for x to be less than 1 in this scenario. X must be 0. And so we actually already computed that. So that's just going to be 1 minus 0.3 to the 10. Right? Again, something you could have figured out without thinking of it in terms of a binomial, but it helps to see that this is actually consistent with what we've learned before. Figuring this out without the binomial would be really tough. You'd have to figure out all these scenarios that could happen. That is an example. Any questions on the example or how it was interpreted or what we did it or anything?
Can we get a refresher for how we pick and choose C in the calculator?
What?
A refresher for how we're supposed to plug NCR into our calculator?
Well, if you have the T, I, blah, 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 first you enter the N, right? So in this case, you first enter 10.
Okay.
Then you press the math button.
Math. Oh, got it. Math number.
And along the top, you'll see a bunch of things. They'll go to the probability tab, the PRB.
Yeah.
And then you'll see NCR somewhere in the list there. It's probably either the third or the fourth item, depending. The different version will have it in a different position.
Okay. And then I got it. I just forgot that we're supposed to put math.
Yeah, NCR, and then you enter the K, which in this case could be 3 or something. So this would be the K, and then you press equal.
120.
Yeah, so there are 120 ways for him to make 3 of them.
So at any given moment, x is always k.
Yes, x is measuring the number of successes. That's how we define this random variable. So we define a function on x. X is counting how many successes we want to find.
So why do we have 2 different variables?
For what?
X and k.
No, k you think of as a fixed number. Right, for a particular question, the k is always just, it's going to be that number. Or it can be these several numbers.
Okay.
X is the general variable that's measuring it, and it takes on the values that we call k for a particular situation. Like I said, the binomial will come back to a situation where it's again necessary, so we'll just move on after this one example. If there are no questions, let's talk about some other distributions. Another important distribution also pretty common is the Poisson distribution. Not poisons, Poisson. It's French, pronounced Poisson. 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 Poisson distribution, it's a French word. It's named after a French guy. You know how the French are. So what situation you use this guy? It's if you know the average number of times something will happen in a certain interval, like a time interval or a certain number of events. You can use the Poisson distribution, right? It has another use. The one thing you're going to realize about the binomial, it's super useful, but a lot of times it's actually hard to actually apply it. So they come up with all these ways to approximate what happens to it. The Poisson distribution was actually a way to approximate the binomial distribution in a certain instance. I think it was when n was large and k was low. In the case n is large. Yeah. But p is small. But it has another use that's really convenient. It's useful all on its own. Right, so you can see the scenario, the binomial is really, really useful, but the thing is if your n is huge, like you're repeating something 100 times, 1,000 times, and then you want the probability of less than or equal to 500, then either way, whether you do the complement or not, that's hundreds of calculations you're going to have to do, right? That's not something you want to spend your time doing. So you can come up with ways to approximate this binomial. And a Poisson is one way to approximate it, but that's not the situation we're going to look at it in. We're going to look at it as a distribution in its own right that will cover a certain situation. And this is the situation. Suppose we expect a certain independent event to occur lambda is the concept we use here because we're math people, like using Greek letters to confuse people. Lambda times in some time interval or space interval
Can you pronounce that symbol?
Lambda.
Lambda.
Called lam and then da. Yeah, it's used in physics for wavelength. Or frequency. One of them. Okay, so lambda is how many times you want something to occur in some given time interval or space interval. Right? So I can say, oh, in a given class I expect to be threatened by Sienna 8 times, right? That would be my lambda. Right? And I want the probability that she's going to threaten me 3 times today. Right? That's sort of the situation where a Poisson would come in handy. Right? So we expect something to happen a certain number of times in some time interval or in some space interval. It could be any interval. We expect this to happen ever so often in terms of this category. Right? We can use a Poisson distribution. If you let x equals number of times the event occurs, then x is a Poisson random variable. And again, I think we use k as the notation. The probability that x equals k, right, that this thing that we're looking for will happen k times, is going to be lambda to the k e to the minus lambda over k factorial. Yes. So that's the formula. We plug that formula into our mean and standard deviation formulas, that thing with the radical and all that stuff. We can simplify it to get this guy with our average, mu, would be lambda, that's how much we expect on average, and our sigma is the radical of lambda. Let's look at an example. I'll probably just talk about it. Don't want to emphasize it too much.
Can you just place E on the apple?
E is your regular, the letter E, the 2.71828. That's in your
Natural log?
calculator. Yeah, the base of the natural log.
Can you just
Can
put
we
that
just
at the
go
bottom?
e to the bottom with the top as e to the lambda?
Yeah, you could. Yeah, you could put E to the lambda on the bottom. They usually write it that way though. I don't know why.
E to the wavelength.
E to the minus lambda. It makes it more confusing that way, so we can keep our 30%. In a certain. Yeah, you gotta keep that 30% quota. Just like throw it up top, make it a negative power. In a certain college dorm, one expects students to pull an average of 21 pranks per day. It's not really Sienna, I put week here. So in a dorm, people pull 21 pranks every week, right? So now, what is the probability that right, so a problem where you need to use a Poisson distribution, we'll start out by talking about sometimes a number of times you expect something to happen on average over some interval, some time interval or some other kind of interval, right? So now A, what is the probability that the students pull no pranks today?
You mean this week or today?
I mean today.
1 out of 7.
So B. A total of 2 pranks are going to be pulled today. C. At least 1 prank is pulled today.
Why is it today? Are you per week over?
That was on purpose. And D, less than 4 pranks are pulled today. So, this is a Poisson distribution. You expect something to happen lambda times in a given time interval. This would be the probability of something happening k times in a certain other interval that you can judge in terms of the original. So, just to sort of walk you through this problem, you know the average per week, right? Now the question's over here, it's talking about a particular day.
So divide it by 7?
So you'll divide it by 7, right? Because here it's by day. So you have to be aware of the interval that you're given, but the interval that you're asked about might be something different. So basically you'll say that, oh, 21 times per week is an average of 3 times per day. So for these problems here, you're going to use lambda equals 3, right? That's going to be your lambda value for all of these, because they're all talking about in a day, right? So in the first one, you're going to have k equals 0, no pranks today. Right, the students turn over a new leaf, sign is absent, so there's no bad influence. So no one pulls any pranks. You use lambda equals 3, k equals 0 into that formula. Here, 2 pranks, right, just put k equals 2, lambda equals 3 into that formula. At least 1, right, it means 1 or more. The thing is, in this case, it can sort of go up forever, right? Potentially infinite number of pranks. So you'll just use the complement, right? 1 minus the probability of no pranks. And then less than 4, in which case you'd sort of do the addition thing again, because again you have mutual exclusivity here. So you just do the probability of 0 plus the probability of 1 plus the probability of 2 plus the probability of 3. And that's that. So you try it on your own. I won't emphasize it. It's not really emphasized in this class a lot, but it is a really important thing. I might put a bonus problem on it, and it'll be an easy bonus problem.
Here, go over it.
Try it on your own. Ask me questions if you get something wrong next time.
We know it's wrong.
Yeah.
You asked me about it.
Wait.
So you should be confident, like, yeah, this is
Yeah.
right.
Okay, wait, hold on a second. What's k then? If lambda is 3.
K is the number of times you're looking for it to happen. So in the first one, k is 0. K is 2. K is greater than or equal to 1. Or k is less than 4.
And
Right? So x is the number of times the event occurs, right? And so x equals k. K is the number of times you're looking for this thing to occur. So given that you know how often it happens on average, what's the probability that it will happen a certain number of times?
And then factorial, how do we even do that?
In your calculus.
Oh, just 2 factorial? I mean, for number 2. Right?
Yeah, 2 factorial would be in the denominator.
Interesting.
So you put 3 raised to the 2 power, e to the minus 3, divided by 2 factorial. 2 factorial is just 2.
Okay, don't worry.
And if you, I think in the TI, if the factorial is not there right away, you still have to go through the probability thing maybe.
It's in the power.
Yeah, you have to go to math, probability, and factorial is going to be one of the options there. Okay, so that actually ends chapter 13. We're going to move on to chapter 14. Things are getting too easy, so we're going to make them more complicated. Forget discrete random variables. We're going to talk about continuous random variables.
Oh joy.
Do you have the answer for number one?
What?
For A, do you have the answer for A? To check something.
It would be 3 to the 0, e to the minus 3 divided by 1.
So just one.
3 to the 0 is 1. E to the minus 3, or it'll be e to the minus 3 is the answer.
E to the minus.
3.
Yeah, 1 over e cubed would be the answer.
Sorry, why is that over 1?
Because 0
0 factorial is 1.
Okay.
Yeah. That's in the definition. Continuous random variables. So the difference between continuous and discrete, remember discrete you could only pick on certain isolated values. Continuous means you can pick on any value in the interval that you want, right? It's kind of like the real numbers versus the integers, right? So that's sort of, you can have infinite possibilities in any interval you want. Okay, so let's talk about how, well, I did mention how it's different here. Let's talk about that. So it's kind of the same idea as discrete random variables. Except now our variables can take on any value in some interval. Clearly, any value, right? So a discrete variable cannot take on any value. So for example, when I gave you that basketball player problem, right? How many baskets he makes couldn't be any number, right? It had to be an integer between 0 and 10, right? You could only pick those 11 possible values, right? You couldn't say he made pi baskets or he made 1/3 of a basket, right? There were certain numbers that you just couldn't pick. There are cases though when all numbers are fair game. You can pick any value in some interval, and that causes a continuous random variable, right? That means you have a continuous streamlined function. Nothing is isolated. You can't write a probability distribution in terms of a table where you just say a few values. It's not good enough, right? So continuous, it kind of complicates things. Not kind of, it gets complicated a lot, but we're not going to go too far with it. It's just 2 and 9, it's not kill ourselves here. So in 375, the majority of your time is going to be spent on things like this if you took one of the serious math major probability classes. Because here calculus comes in and you have integrals and double integrals and all sorts of craziness. Let's actually move on. The best way to measure things here is called a probability distribution function, right? Which the function in this case will be continuous, at least in some intervals, no? So probability distribution function, or it's abbreviated PDF. Or you might see it being called a probability mass function. Which is PMF. Instead of or, I could say AKA, so you know it's referring to the same thing. So it's just a function, and I can tell you about the function. It has, sorry, it's not distribution, it's density. Density or mass. Okay, the function follows these criteria. All right, so how do you know if a function is a PDF, or what makes a good PDF? So remember when we were talking about probability distributions for discrete random variables, we could put it in a table, and then the sum of all probabilities must be 1, and then each individual probability must be between 0 and 1, right? So there are certain things that we were looking for to happen to know that it's a bona fide probability distribution. In the same way, there are certain things we're looking for to happen here with this function. I can't just randomly define a function. Like I can't just say y equals x squared is the PDF for this, right? I can't really do that. The function has to fulfill certain criteria. So a PDF for a continuous random variable x is a function f of x for which a f of x must be greater than or equal to 0 for all x. Right? So it's measuring a probability, so it has to be 0 or bigger. B, the area under the graph from minus infinity to infinity must be 1. You did definite integrals in 205. Your lower limit could be anything, your upper limit could be as big as it wants. But when you take the limit on the entire real line, the area under the curve must be 1. When you do the integral on the real line. And C. The area under the graph actually corresponds to probabilities. So if we know for a fact that the probability that x is between some values a and b is given by the integral from a to b of f of x dx. The probability that x is between a and b is given by that integral, the area under the curve. In case you forgot what a definite integral means, let me actually write that out. It means the area under the curve.
Yeah.
i.e., the probability that x is between two given values is going to be the area under f of x between x equals a and x equals b. FYI, since we're talking about integrals, it does not matter if we use this or that, or this or that, right? Because the area for a single point, the area under a single point is nothing, right? So it really doesn't matter if we're including or not excluding the endpoints. It's not going to matter because there's no area under it. Okay.
I don't know what's going on.
That's fine.
Yeah.
That's completely normal. Don't worry.
What's completed? It's even over 10 years.
Symbols, I don't know.
It's calculus. It's an integral sign. What are you talking about?
Math is that subject where as soon as you like peel over the wound, it rips
It
the
does.
back off.
Yeah.
I looked away for 1 second, and you came up with all this.
Yeah, you're like, oh yeah, binomial, yeah, that's cool, yeah. Oh, Poisson, yeah, that's cool, all right, this is not so bad. Boom, oh my god, math again, damn you.
You blink too long and you're lost. That's college.
1 second.
Hope no one blinked. Well, see, Saina's gonna have like a really fun surprise when she gets back. She's gonna be like, so what did we do last time? Okay, so let's do a random kind of thing here. I'm just, for emphasis, let's say these two guys here are 0.2. I'm drawing a probability histogram, probability here versus some x value here. Let's say those two are 0.2, make them 0.1. Let's make these two 0.2. And that would make this what? So these are 2.1, so they add to 0.2s. This will make 0.6. So this would be a 0.4, right? So let's pretend we were in a discrete random variable and this was a probability histogram, right? So the probability that x takes on the value 1 is 0.1. The probability that it takes on the value 5 is 0.1. The probability that it takes on 2 or 3 is 0.2. The probability that it takes on 4 is actually 0.4. Now the idea is the width don't change when you're talking about probabilities. So you can sort of just make it a unit where this length here is 1, right? The length of each rectangle is 1. And so what you can do is you can sort of think of a situation where if you ask about what's the probability that x equals 4, for example, in this case, you can literally think of that as the area of this rectangle, right? You have a 1 times a 0.4, right? Or if I can think of, so this is the area of rectangle about 4. Or I could think of something that the probability that x is between, say, 3 and 5, right? Well, that would just mean that probability of x is 3 plus the probability of x is 4 plus the probability of the x is 5. And what we would do here is you could literally just think of the area of being between 3 and 5. You add up all the areas of all these rectangles, it's the same as adding up the probabilities. So that would be 0.2 plus 0.4 plus 0.1, which is 0.7. So a continuous random variable x exists. So now it's like, on your probability, you just have this curve that's doing whatever. Between some values A and B. Now sure, you can approximate if you want to figure out, oh, what's the probability that it's between some values here, like A1 and B1. You literally want to measure the area here. We know how to measure areas of a rectangle, so what we do is we dice this into a bunch of rectangles, which reminds you of a Riemann sum from calculus, and then you end up with an integral. Basically, the same way that you can find probabilities by finding an area under a histogram. If you didn't have a histogram, you had this random curve that fulfilled all those properties that we had before. The integral, the area under the curve, gives you the probability of that region. Right? And there are several scenarios for which we can do this. Did I introduce one yet? Examples. There's something called a uniform distribution. This is a continuous distribution. So here's what a uniform distribution would look like. This is just the function that it's always just a flat line. The PDF is so in a problem, they'll usually tell you that, hey, this is uniformly distributed. It means the probability is always the same. So basically that means that the picture that you're looking at here, between A and B, it's just going to be a flat line. It's always a constant. And that line is at the level 1 over B minus A. So basically your picture here is just one big rectangle. So it's a continuous rectangle. You can pick any number between A and B that you'd like, or any region between A and B that you'd like.
You should be here.
Outside of it, you're 0, so there's nothing going on here. This function actually forms a PDF, because what's the area of this rectangle? It's B minus A, which is the length, times the height, times 1 over B minus A, you get 1, right? The area under this curve from negative infinity to infinity is 1. Right? So this is a uniform distribution. So here you're measuring the probability, and here you're measuring your x values. So, for example, the probability that x is between something like x1 and x2 is going to be say I have this rectangle, my x1 value is here, my x2 value is here. I literally want the area under that curve.
Uh-oh,
What?
I messed up my notes. Sorry.
Area is equal to that probability. Right? And it's just the rectangle. So length times width would be how you do it. Length times height. I'm sure we'll have time to get through the examples, so we'll end today's class with everyone being thoroughly confused.
Oh, I thought you were gonna say right now. It's like, wow. That's
I'm not nearly as confused as I usually am.
Or have you gotten used to being confused?
Maybe.
It's like, I'm not, she's not perturbed, I'm not upset, I'm not anxious, nothing. This is,
I feel like no emotion.
I live here now. I live in the land of confusion. Like, the neighborhood's familiar, I know all the neighbors. I'm comfortable here now.
That's very accurate.
It's like, yeah, I feel fine, Jhevon. I don't know what you're talking about.
I feel like no type of emotion. You all look really stressed, and I'm just chilling. But I still have no idea what's going on. So like,
I don't worry. It starts out that way. It'll get easier, don't worry.
Beginning of the semester.
What?
That's what you said at the beginning of the semester.
And it was the truth. Like after the first test, everyone's grade went like that. I didn't like. Now I have to like get back to the 30% because now it's like everyone's passing. Like, jeez. I'm like, I have to make up all this stuff now. Just see how many people I can confuse.
imagine at the end you're just like, just kidding, guys.
Like, oh yeah, you don't really need to know any of that actually. That would be so mean.
No, imagine you were like, I just wanted to see how far I could get. Just to see how long it would take me.
You guys just follow me, okay.
How was funny this?
fun. A lot of fun.
Just to use the language that you might see in a problem. Probabilities are uniformly distributed. The good thing with the continuous distributions is that they usually tell you when they show up.
Wait,
They'll say, hey, this is Poisson distributed. Hey, this is uniformly distributed. Hey, this is normally distributed. They're actually going to tell you when they show up. Something like a binomial or any other discrete random variable, they're not going to tell you. They expect you to be able to figure it out. But this one is kind of iffy. So they'll usually just tell you outright, oh, this is uniformly distributed. Basically what that means is the function looks like this. It's a rectangle. Example.
When I don't know what's going on the test, I'm just gonna write the pronunciation of Poisson. At least I asked
It's
something.
pronounced Poisson. You write the phonetic. Suppose a uniform random variable has PDF. Alright, so this is the function that gives the probabilities. It's a half when my x value is between 3 and 5. And it's 0 otherwise. Okay, so they're going to tell you, hey, this is a uniform distribution. This is how the probabilities are distributed. So as long as your x value is between 0 and 5, the probability of that happening is a half. And outside of that range, it's impossible to be outside of that range. Okay, so they'll tell you that. So that means it's uniformly distributed. This means if you're between 3 and 5, the probability should always be a half.
Yeah.
What's going to be the height of this thing?
1/2. I mean half. Is that something?
Well, it's going to be 1 over the b minus the a. That's always what it's going to be. So it's 1 over 5 minus 3, which is 1/2. Turns out to be the probability. Right? So no matter where you are between 3 and 5, the probability is a half when you're in that range. Okay, so that's basically what we're looking at. Now, here are some questions. Compute A, the probability that x equals 4. B, the probability that x equals 3. C, the probability that x is between 0 and 1. D, probability that x is between 3.5 and 4. E, the probability that x is strictly between 3.5 and 4. F, the probability that x is between 4 and 6. Look at 8. What's the probability that x is 4?
Probability that.
So here we are on our graph. 3 and 5. And this is up to a half. And we want to know, what is the probability that your x value is this value?
This is the probability of 3 is less than x, less than 5. This is probably a 3 because the probability of 4 is probably 5.
No, you're thinking discrete. It's not discrete anymore.
No.
I can pick literally any number here. Okay, so what does that tell you?
Can you
0.
draw a line? What?
Probability is the area under the curve. What's the area under this line?
There is
Under
none
what
because it's a
curve?
horizontal line.
There's none. Like, the line doesn't have an area.
Vertical.
I understand.
What's the probability that x equals 3?
0.
It's also 0. The probability of getting any specific value is impossible. It's super hard.
But I thought it was half.
No. The probability corresponds to the area under the curve. There is no area under just 3.
I have another question.
Yeah.
Are D and E the same thing? Because you said less than and equal to and less than?
Yep.
Okay, cool.
What about C though?
It's 0 too.
So I want the probability that x is between, what, 0 and 1?
Yeah.
So here's my picture. Here's my rectangle over here. This is 3, this is 5. I want the probability that I'm between 0 and 1, which is over here.
0.
0.
0.
It's non-existent.
There's no area.
So why do you have a
Because he just
rectangle?
wanted to waste our...
Because I just wanted to waste your time. Okay, let's do D.
2K16 waste students' time. Waste his time. Yeah.
Probability that x is between 3.5 and 4.
Why is that?
What's that going to be?
0.
Let me guess. 0.
No.
No, oh my god! As soon as he said 0 the first time, it wasn't
Would it
0.
be that divided by?
4.
Yeah.
3.5.
So 1/4.
How do you get 1/4?
It's half times half.
Right, how do you get half times half?
4 minus 3.5 times half, which is then
Right, so we want to go from 3.5, which is right here, all the way up to 4, right, which is right here. So what I'm looking for is I'm looking to be between this range, which means
One
I
base
want my x value to be somewhere in this interval. but my curve is at a half, so I need the area under the curve. So this length here is a half. Length times width is a half. So this is going to be the probability of being between a 3 and a 5, 3.5 and a 4 is going to be a half times a half, which is 1/4. The area under the curve, right? When you're in continuous probabilities, that's how you think of a probability. The area under the graph that you know corresponds to the distribution that you're talking about.
Okay, I have another
You should
question.
start off with this first.
But remember, at the what?
You should have started off with this first, because everybody's like, what are you talking about when you were talking about levels? I don't know.
Yeah, but it wouldn't have like
Yeah, torture, okay.
you know that you wouldn't have gotten that. Cause then I do this and then I do that. That'll be like, yeah, it's too. You know, it's less suspense. Come on, sometimes you gotta.
Wait, Jhevon, I have a question. So the curve is the square, the rectangle that you draw, correct?
Yeah, this is the function is here.
It's just the top line.
It's just the line.
Okay, cool.
Yeah, I just drew this for emphasis.
Alright.
Meaning
I was like, I don't see a.
we're vertically looking.
Oh.
Yeah, for E, again, it's the same as D, right? Because if you're looking at area, the lines at the ends have no area to them, right? There's no thickness to a line. What about F? What's the probability that X is between 4 and 6?
Wait, we're in E.
He's a
Oh.
statement.
Same as D, because the endpoints don't matter. Remember, whether I'm including them or not doesn't matter, because the probability of any particular number is 0. So whether I include the endpoints or not, irrelevant. So again, remember this is half. Now where do I want to be?
What's F saying?
Between 4 all the way up to 6. Now what is the area under the curve between 4 and 6? Well, there's this area here. But then the curve is 0 over here, so that contributes nothing.
So, it's
So
one
what's
half.
this going to be?
One
That length
half.
here is 1, and then there's a half. So this is going to be 1 times a half. So there's actually a 50% chance that my X value will be between 4 and 6.
Because it's independent. Wait, say that one more time.
What?
You said that the answer is.
I want the area under the curve between 4 and 6.
Okay.
But only this part has area. That part is 0.
So it's 1 plus 0. That's
So
at the
just,
bottom.
no, I want to find the area of this.
So it's 1 times 1/2.
Yeah, so area of a rectangle. For uniform distributions, you're just finding areas of rectangles.
That's
That's basically what it comes down to. Right? Yeah, so that's pretty much the easiest kind of continuous distribution you have. We'll make things more interesting next time.
No.
Right? But the main concept I want you to get is for continuous probability corresponds to the area under the curve. There's going to be a curve that's going to describe your probability. And when you find the area in a certain interval, that gives you the probability of being in that interval. That concept is going to be super important next time, and we'll use those normal distribution tables. So bring it next time. We didn't get to it.
Can I print them out on the internet?